The options for the nature of the image are real or virtual. In order for the image to be a real image, the reflected rays must converge to a point. They actually must come together at some point. That's what's happening in this particular ray diagram. These three reflected rays actually do come together at that point. In other words, they converge together. On the other hand, if I had a virtual image, the three reflected rays would diverge. But for this particular image, the nature of this image is real. Now, to talk about the size of the image, I need to compare how tall the image is compared to how tall the object is. So I could take a ruler and actually physically measure the height of the object. In this case, it's 3 centimeters high. I would call that height HO. Likewise, I'm going to measure the height of the image, and I'm going to call that HI. When I measure that height, I find that this image has a height of 1.5 centimeters. In other words, the tip of the image arrow is 1.5 centimeters from the principal axis. Since HI is smaller than HO is, then I say that the size of this image is reduced. The other option would be enlarged or magnified if the image height was taller than the object height. Finally, there's orientation. Which way does the object and the image point with respect to each other? If they have the same orientation, we say that the image is upright or erect. On the other hand, if they have opposite orientations, then we say that the image is inverted. In this case, the object and the image have opposite orientations. The object arrow points up to the top of the page, whereas the image arrow points downward to the bottom of the page. This image is inverted. Now, sometimes you're going to be asked to find numerically what the image distance is away from the vertex of the mirror. And the object distance you'll have to set as well. In this particular diagram, you'll see that I've made the focal length 5 centimeters, that the center of curvature is 10 centimeters away from the vertex, and the object distance is 15 centimeters. And you can see on this diagram that the image is located 7.5 centimeters away from the vertex. So you want to draw these diagrams to scale. You want to use a ruler to help you to do them. Then use ray tracing to help you locate geometrically and classify the nature, size, and orientation of these images. Let's take a look at the 3 examples that are in your textbook. An object 1 centimeter tall is placed upright on the principal axis of a concave spherical mirror at a distance of 5 centimeters from the mirror. The radius of curvature of the mirror is 6 centimeters. Draw a scale diagram and use ray tracing to determine the location, orientation, and height of the image. I start by sketching a to-scale diagram showing the mirror, the focal point, the center of curvature, and the object. So here's the information that's given in this problem. The object is 5 centimeters away from the mirror. The radius of curvature is 6 centimeters. So that means that the center of curvature is 6 centimeters away from the vertex of the mirror. First of all, I got to figure out what's the focal length. And I realize that the focal length is half of the radius of curvature. So the focal point is going to be located at the 3 centimeter point. Now from there, I need to draw my 3 principal rays, and I think that this problem wants a numerical value for the height of the image, so that's something that we're going to need to find as well. So I have tried to draw a scale diagram. I've got 2 check marks for each centimeter, and my object, while it's 2 centimeters tall in my actual diagram, represents 1 centimeter in this particular problem. So let's sketch the 3 rays. There's the first ray. There's the second ray. We can already see an intersection point that's near 7.5 centimeters on this diagram. Now the third ray presents kind of a problem because I need to hit the top of the object and the center of curvature, and I need to hit the plane of reflection. Well, this ray looks like it's going to miss the mirror completely. Well, that's okay. I'm still going to connect those 2 points and realize that the reflected ray is going to come back on itself. So I'm going to pretend like the mirror is large enough that it would actually have this ray strike it. In reality, this ray would not strike it, but for diagramming purposes, we're going to pretend that it does. So there's the incident ray, and the reflected ray comes backward on it, so that it strikes at that point right there. The tip of the image arrow is located where those 3 rays intersect with each other. That's going to be where the tip of the image arrow is and the tail sits on the principal axis. The nature of this image is real because the rays converge together. The size of this image is enlarged or magnified because it is taller than the object is. And the orientation of this image is inverted because it is pointing in the opposite direction as the object arrow. Now, we're asked to find the location of the image, and you'll see that on my scale diagram, the image is located almost exactly 7.5 centimeters away from the vertex of the mirror. If you were to do this algebraically, you would see that it is exactly 7.5 centimeters. So I'm going to say that the image distance is almost 7.5 centimeters. And if you measure this with a ruler, what you're going to find is that the image is almost exactly 1.5 centimeters tall. And in fact, if you did this algebraically, you would see it's exactly 1.5 centimeters tall. Let's take a look at the next one. An object 1 centimeter high is placed upright on the principal axis of a concave spherical mirror 8 centimeters from the mirror. The radius of curvature is 6 centimeters. Draw a diagram and use ray tracing to determine the location, orientation, and height of the image. We begin as we did before, sketching a scale diagram and showing the things that we know. So here are the things I know. Again, I have sketched my principal axis. I have labeled the tick marks there to indicate how many centimeters things are away. I need to figure out what is the focal length of this mirror. The focal length is half of the radius of curvature. Since the center of curvature is at 6 centimeters, the focal point is going to be located at 3 centimeters. Now I sketch my 3 rays. There's the first ray. There's the second ray. You can see the intersection point of those 2 rays is just beyond 4.5 centimeters on this diagram. Now you can see I run into a similar problem again. The top of my object, the center of curvature, are going to cause a ray that will miss completely the mirror. But again, I'm going to sketch that ray anyway as if that ray would hit the mirror, and we'll see where that intersection point is. You can see that these 3 rays intersect almost exactly that point right there. And so the image is going to be located at that point. If I look, it looks like that image is located about 4 3/4, maybe a little bit more, 4.8, 4.9 centimeters away from the mirror. And if you do the problem analytically, you'll find that it is exactly 4.8 centimeters away from the mirror. If you measure the height of the image, you see that it is just above 0.5 centimeters tall. And in fact, analytically, you get that the height of the image is 0.6 centimeters. Now let's classify this image according to its nature, its size, and its orientation. Because this image is formed by the reflected rays that actually do come together, these reflected rays converge, so this is a real image. Because the image is shorter than the object is, then the size of this image is reduced. And because the image arrow points the opposite direction from the object arrow, the orientation of this image is inverted. An object 1 centimeter tall is placed upright on the principal axis of a concave spherical mirror at a distance of 1 centimeter from the mirror. The radius of curvature of the mirror is 6 centimeters. Draw a scale diagram and use ray tracing to determine the location, orientation, and height of the image. Now, let me make a comment at this point, and that is that these ray diagrams are probably going to take up a lot of paper. So you just need to dedicate a lot of paper to it, a lot of space. If it takes a whole page for a single diagram, so be it. That's just the way these problems go. You're also going to find that you'll probably make several false starts in trying to figure out where to place the diagram on your paper in order to make it fit. And what you may find yourself doing is taping extra paper to your diagram or re-sketching your diagram. I wish your authors had gone ahead and given you the analytical equations for determining what the location and the height of the image is going to be. I'm going to go ahead and give that to you at this point. I'm not going to introduce them mathematically until we get to that lesson, which is lesson 54. But if you want to cheat, here are the two equations. The first one is called the lens equation or the mirror equation, and the second one is called the magnification equation. The negative sign we'll talk about in a later lesson. It actually tells you something about orientation or the nature of the image, and we'll have a whole list of sign conventions that we'll deal with. So if you want to actually calculate and then figure out how to sketch your diagrams, those are the equations that you're going to use. I'm going to stick with the ray diagrams at this point and then teach you the equations a bit later on. Again, we begin with the things we know. I've sketched my principal axis to scale. Now you'll notice that I've sketched some negative numbers on this, and the reason will become apparent fairly soon. I need to figure out what is the focal length of this mirror. Looks like these three examples have shown mirrors with identical focal lengths. That will not always be the case. The focal length is half of the radius of curvature, so the focal point is located at the 3 centimeter point. Now I sketch my 3 rays. There's the first ray. The second ray actually presents a little bit of a problem because the second ray leaves the top of the object and travels as if it's going to go through the focal point. But the focal point is behind it. That's okay. I'm going to sketch those 2 points, take the ray and extend it toward the plane of reflection, and then wherever it hits that plane of reflection, I'm going to sketch the reflected ray as if it reflects from that point. So there's the incident part of that second ray, and there's the reflected part. Now the third ray. So now I've got 3 reflected rays. Ray number 1, ray number 2, and ray number 3. But those 3 rays don't actually come together. Those reflected rays diverge after they hit the mirror. And so for that reason, we're going to say that the nature of this image is virtual. Now we've actually got to locate the image. And to do that, what I'm going to do is I'm going to go back to the reflected rays and trace backwards on themselves until they are behind the mirror, and we'll find that they will intersect at a certain point behind the mirror. So let's do that one by one. I'm using dotted lines to trace these rays backwards on themselves. That indicates that the image is a virtual image. I'm having to extend those rays backwards with my eye when I look at them. There's the second ray, and now I need to do the third ray. And now I see that these 3 rays have intersected at that point right there. Here is where my image is located. We can see that the size of this image is enlarged because it's taller than the object is. And we also see that the orientation of this image is erect or upright because both the object and the image arrow point in the same direction. Now I need to locate and measure. I need to figure out where is it behind the mirror and how tall is it. Now on my diagram it looks like it's just beyond 1.5 centimeters behind the mirror. If you do the mathematics, what you find is that it's exactly 1.5 centimeters behind. So the image location is about, well, in this diagram 1.75, but between 1.5 and 1.75 centimeters. The height of this image is 1.5 centimeters, and that's actually what the calculation gives, 1.5 centimeters tall. So let's summarize what we've done. We have used ray tracing to locate and classify images produced by concave mirrors. There are 3 principal rays that we use of the infinite number that come from the object. Those 3 rays we trace and then extend, if we need to find where the 3 reflected rays intersect. That intersection point is the tip of the image arrow, and if we've drawn scale drawings, we can measure distances to figure out what is the size and the location of the image, and we can classify the image according to its nature, its size, and its orientation.